So the situation here is that there is a lighthouse. We'll say it's here. There's the lighthouse. And it's 2 miles from some shoreline, right? And it's this miraculously straight shoreline. I'm real happy with that because that makes the math easier. It's 2 miles from a shoreline, which means at the right angle. And the beacon of the lighthouse, right? So the thing that's actually shining the light revolves or is moving. So it might be shining here in one direction, and then it moves. So now eventually it's looking in this direction. Right. So this is now an angle, right, theta, that the beacon has moved. And this thing's revolving at a rate of 6 degrees per second. So the rate of change of the angle of the beacon directly to the shore is 6 degrees per second, which is unfortunate that they're using degrees, right? We'll have to make note of that. Everything needs to be in radians in calculus. How fast is the light being moving along the shore at a point 3 miles from a point on the shore closest to the lighthouse? So we want to know what is exactly the rate of change of this. Here. Right, so it also has a rate of change in this direction, the light. And if this is the distance x, what we want to know is what is dx dt. How fast is the light on the shore moving, given these parameters. We want to know a specific value when it's 3 miles from that point. So a couple things that are problematic for us. One, d theta dt is in degrees per second. And we can't work with that. We need to convert this to radians. So 6 times pi over 180 helps us remind us that the rate of change is pi over 30 radians per second. So this is d theta dt in radians, and that's important. Then we need a way to relate these things. So again, back to our picture. This is changing. This is x. It's changing in this direction. This is 2. This is theta. So I've got an angle. I've got the side opposite the angle. I've got the side adjacent to the angle, which means that the opposite over the adjacent must be equal to the tangent of the angle, or also x must equal 2 times the tangent of the angle. Right? This is the relationship between the things that are changing. When we take the derivative of this with respect to time, we will find that 1 dx dt equals 2 times the secant squared of theta d theta dt. Alright. Now, some of you are familiar with this identity, 1 plus tangent squared theta equals secant squared theta. And so you'll be able to use that to figure out secant squared theta. Others may need to convert secant squared and think of it as 1 over cosine squared. Right? And either way will work. I know for myself, I'd probably think about it in terms of cosine. So let's go back to our drawing so we know how to substitute. We want to know specifically when x equals 3. And since I know I would need to think about this in terms of cosine, this means that in that right triangle, 2 squared plus 3 squared equals the hypotenuse squared, or the square root of 13 is the hypotenuse. So that means that the cosine of theta, since it's adjacent over a hypotenuse, would be 2 over root 13. And this means that cosine squared of theta equals 4 over 13. Right? I probably would not think about the tangent secant Pythagorean identity, but I do think a lot about cosine and sine. Right, so I'm going to use this. This means that in terms of my problem, I happen to be working with dx dt equals 2 times 1 over cosine squared theta times d theta dt. And what we want to know is dx dt. We just found at the point in question the cosine squared of theta is 4 over 13. So 1 over cosine squared theta must be 13 over 4. And we're told from the beginning that d theta dt is 6 degrees per second, or in radians, because we converted it, pi over 30. We need that to be pi over 30 because we're always working in radians in terms of calculus. This means that dx dt must equal 13 pi over 60. And what are the units on this? They're miles per second. And make sure you see why. If you're not sure why, notice that our cosine has to be in miles because the 2 was in miles and so is the 3. So when we solve for the hypotenuse, square root of 13, that's also miles. Pi over 30 is, yep. So there we are. This means that our answer in words would be the rate of change of the light on the shore when it is 3 miles from from the closest point is 13 pi over 60 miles per second.